Hello guys, we're going to start our sixth lecture on transform calculus and partial differential equations. So in this lecture, I want to talk about Laplace inverse. So far we could find Laplace transform of some functions. I brought these functions here and the Laplace transform because in the exam, so I will provide you with this table. So we said when function is equal to 1, Laplace transform is 1 over s. We found Laplace transform of t to the power of n is n factorial over s to the power of n plus 1 e to the power of at. So we said the Laplace transform is equal to 1 over s minus a. Sine kt is k over s squared plus k squared. Cosine kt it's s over s squared plus k squared. Sine hyperbolic kt, we didn't talk about sine hyperbolic because you know sine hyperbolic, for example, sine hyperbolic of, let's say, kt, it's equal to e to the power of kt minus e to the power of minus kt divided by 2. And you know how to find Laplace transform of e to the power of kt and e to the power of minus kt. As a result, it's very easy to find it. Laplace transform of sine hyperbolic kt is k over s squared minus k squared. Cosine hyperbolic kt is e to the power of, is s over s squared minus k squared. We talk about t to the power of alpha, so we use gamma function to find Laplace transform, and that's it. As a result, for example, if I ask you find Laplace transform of t cubed, so you can easily go to the table. You say, okay, I have it here, t to the power of n is 3. As a result, Laplace transform is 3 factorial divided by s to the power of 3 plus 1. So 3 factorial is 3 times 2 times 1, so it's 6. And s to the power of 3 plus 1 is s to the power of 4. Using the table, you can easily find Laplace transform of function. Now I want to ask you another question. If I ask you, I say I have one Laplace transform, it's 6 over s to the power of 4. This function is Laplace transform of what function? In other words, what's Laplace inverse of 6 over s to the power of 4? It means that 6 over s to the power of 4 is Laplace transform of what function? So what you have to do, you have to go to this table again. So here you can see that the function which is close to 6 over s to the power of 4 is this one. So if I plug n equal to 3, so we have 3 factorial over s to the power of 4. As a result, we can say that Laplace transform of 6 over s cubed is t to the power of 3. So we can do for everything. For example, if I ask you what's Laplace inverse of, let's say, 2 over s squared plus k squared, which is 4. So again, you go to the table, see which one is close to this function. So here we have s squared plus k squared. It's very close in denominator. If I have k equal to 1, so we have 2 over s squared plus 2 to the power of 2 is 4. So it's exactly the function that I have. As a result, I can say that this Laplace inverse is equal to sine 2t. It's a Laplace inverse. Laplace inverse has some properties like Laplace transform. The main property of Laplace inverse is that a Laplace inverse is a linear transform. So what does it mean? It means that Laplace inverse of alpha times f capital S plus beta g capital S. So alpha and beta, they are two constants, is equal to alpha times Laplace inverse of f capital S plus beta Laplace inverse of G capital S. So it's equal to alpha times ft plus beta times G. So as I already said, alpha and beta, they are constant. Now we use definition of Laplace inverse and the linear property of Laplace inverse to solve some examples. First example. In the first example, you want to find Laplace inverse of this function, 1 over s squared minus 48 over s to the power of 5. The reason that I have table here, because in your exam you have this formula sheet, so you have access to all these formula. So if you want to find Laplace inverse of fs, it's equal to Laplace inverse of 1 over s squared minus 48 over s to the power of 5. So Laplace inverse is a linear transform. As a result, I can say it's equal to it's a Laplace inverse of 1 over s squared minus 48 Laplace inverse of 1 over s to the power of 5. It's equal. So we have 1 over s squared here. We have to go to the table. We can see that in the second function, so if n is equal to 1, we have 1 factorial over s to the power of 2. As a result, Laplace transform of t is equal to 1 over s squared. So we can say that Laplace inverse of 1 over s squared is equal to t. So it's equal to t for the first Laplace. So the second term, so we have denominator, we have s to the power of 5. We have to go and see which one it's close to this function, the Laplace transform. So here we have s1, here we have sn plus 1. If I consider n equal to 4, so I have s5, s to the power of 5 in denominator. But in this case, we have to have n factorial. So we have to have 4 factorial in numerator. But in this case, we have just 1. As a result, I rewrite this Laplace transform like this. So I say it's equal to 48 times Laplace inverse of s to the power of 5. So I consider 4 factorial here. 4 factorial is 4 times 3 times 2 is 24. And I divide by 24 here. In fact, these 24 cancel these 24, and I will end up with this 1. So in fact, I just wanted to make this function like one of these functions that I already found Laplace transform. So the second function, if I consider n equal to 4, so we have 4 factorial over s to the power of 5. Now we have it here. So we can say it's equal to, so we already have t. 48 divided by 24 is 2, and 24 over s to the power of 5 is Laplace transform of t to the power of 4. So we could easily find Laplace inverse of this function. Let's solve another example. We want to find Laplace inverse of two s minus 6 divided by s squared plus 9 is equal to Laplace inverse of, so I can decompose it. So we have 2s over s squared plus 9 minus Laplace inverse of 6 over s squared plus 9. So I just factor out 2. So we have 2 Laplace inverse of s over s squared plus 9. And here we have minus 6 Laplace inverse of 1 over s squared plus 9. Now we look at the table. So we want to find Laplace inverse of s over s squared plus 9. Let's go to the table and see which function is close to this function. So here we have s in denominator, we have s squared plus k squared, but in numerator we have a number, but here we don't have a number, we have s. In the next one we have s squared plus k squared in denominator, and in numerator we have s. So it's very close to this one. If I consider k equal to 3, so the Laplace transform is exactly this one. As a result, I can say that Laplace transform of s over s squared plus 9 is equal to cosine 3t. So we have 2 times cosine 3t, because in this part I have to consider k equal to 3, and then I can see that I have Laplace transform exactly like what we have here. So for the second part, minus 6. So we have 1 over s squared plus 9. I go to the table. I have s squared plus k squared, but in numerator we have a number. So here we have a number, but number, if I consider k equal to 3, because I have s squared plus 9 here, so k should be 3. In numerator I have to have 3. As a result, I write it like this. I say it's equal to Laplace inverse of 3 over s squared plus 9, and I divide it by 3. So now these 3 by these 3, they cancel each other. But now this Laplace transform is Laplace transform of sine 3t based on the equation that we have here on top. So it's equal to, we already had 2 cosine 3t minus 6 over 3 is 2, and Laplace inverse of 3 over s squared plus 9 is sine 3t. So we could find Laplace transform of 2s minus 6 divided by s squared plus 9s squared. Now we go to solve another example. In this example, you want to find Laplace inverse of 3s plus 11 divided by s squared minus s minus 6. So we have Laplace inverse of 3s plus 11 divided by s squared minus s minus 6. So if I look at the denominator and then check the table to see if we have something close to this denominator, so the first part we don't have it, the second one we just s to the power of n plus 1, no, the third one doesn't work, fourth one, fifth one, sixth one, seventh one, none of them is working, because we don't have something like s squared minus s minus 6. In this case, what we have to do, I can represent this function like this. So I say it's equal to Laplace inverse of 3s plus 11 over s minus 3 times s plus 2 I just factor denominator, and I can say it's equal to Laplace inverse of, so I represent this function like this, 4 over s minus 3 minus 1 over s plus 2 is equal to. So now I can easily find Laplace inverse of 4 over s minus 3 and 1 over s plus 2. So it's equal to Laplace inverse of 4 over s minus 3 minus Laplace inverse of 1 over s plus 2. It's equal. So I can factor out these 4, so I just put it here in order to simplify it. So now I look at the table, and here I have 1 over s minus 3. In denominator I have s minus 3, so I have to see it's close to which Laplace transform. So here we have it, 1 over s minus a. So if I consider a equal to 3, so we have exactly 1 over s minus 3. As a result, Laplace inverse of 1 over s minus 3 is equal to e to the power of 3t. And we have 4 times e to the power of 3t, and minus 1 over s plus 2. Again, we are in this category if I consider a equal to minus 2. So the Laplace transform here is 1 over s plus 2, because minus times minus is plus. So it means that Laplace inverse is equal to e to the power of minus 2t. So we could find Laplace transform of this function.